Precalc 5.5, we're going to talk about some more identities here. So first off is the double angle identities. As you can see here, what we have is we have sine, cosine, and tangent, where if I have sine of 2 theta, tangent of 2 theta, and cosine of 2 theta. Sine and tangent both have only one option. Cosine has 3 options that you guys can choose from. And so you always choose the one that's advantageous for the given information that you have. So our example today is going to be if you're given that cosine theta is 3/5 from 0 to 2 pi, or pi over 2, that is 0 to 90, so first quadrant. Can you tell me the sine of 2 theta, cosine 2 theta, and tangent of 2 theta? So the first thing you want to do is you're always going to start off with writing out what you are given and trying to find. So I'm given the fact that I want to find sine of 2 theta. I don't have a double of theta. I only know what theta is. Right here it tells me that the cosine of theta is 3/5. I only know theta. I don't know sine of 2 theta. And so if I go here and say, hey, wait a minute, I have a formula that can break it down into just theta. So that'd be 2 sine theta cosine theta. Now I know cosine theta, so I know 2. 2 is easy. Cosine, hey, that's 3/5 because that's what it tells me. The only thing is I don't know what the sine value of theta is. So to do these, I actually need to create a triangle. So we've done this before. Now it says we're in the first quadrant, so I can build my triangle in the first quadrant. Remember, theta always is at the origin. And then I use my ratio of 3/5 of cosine, which is adjacent over hypotenuse. That's 3, 5. And then you guys should hopefully recognize that this is a 3, 4, 5 triangle, or you can use Pythagorean's theorem to find 4. And so the sine of this particular triangle is opposite over hypotenuse, or 4/5. And if I put 4/5 in, I now have it. And 2 times 4 times 3 is 24 over 5 times 5 is 25. The next one we need to find is cosine 2 theta. Now, when I say cosine 2 theta, I'm looking at my 3 options. Now, we've talked about this before, that I don't generally like to use data that I have created to find some new things, because a lot of times those things that we find are not necessarily accurate. They always got some square roots in it, things like that. This example, yeah, they're nice numbers. So I'm actually going to use the second version because it deals with just cosine. And so when I do this, I'll have 2 cosine squared of theta, because I know cosine theta. So that's 2 times something squared minus 1, and that is 3/5. And so it's 2 times 9 25ths minus 1, or 18 25ths minus 25 over 25, because a common denominator is negative 7 25ths. Now this should make sense that if I'm in the first quadrant, if I double theta, I very well could be ended up into the second quadrant. Now that would also mean that theta would have to be bigger than 45 degrees, because if it's bigger than 45 degrees and I double it, it's bigger than 90, I'm in second quadrant, and second quadrant is where theta, or cosine, would be negative. Okay? And the last one I have to do is tangent of 2 theta. And tangent of 2 theta only has one option. And I'm going to go back to that triangle that I created to find my numbers. So therefore, I end up with 2 times something over 1 minus something squared. And tangent, going back up to here, is 4 over 5. So 4/5. Oh, not 4/5, sorry. 4/3. Opposite over adjacent, and 4/3. So this becomes 8/3 over 1 minus 16 ninths. Or, I'm going to move over here, we end up having 8/3 over 9 minus 16, which is a negative 7 ninths, which equals, running out of room, 8/3 times 9 over 7 negative. Cross out 3 or cancel out 3. Negative 24 over 7. And there we have it. Next up, we're going to do lowering of powers or power reducing identities. Basically says that if I have the sine squared, cosine squared, or tangent squared, we could use the Pythagorean identities to reduce these, or I can use these to get rid of any exponents in general. And so, using these just like any other identity, we can start off with cosine to the fourth. Cosine to the fourth, remember, is cosine times cosine times cosine times cosine. So we should be able to group that up in other ways, like cosine squared x times cosine squared x. Each one of these now follows that pattern. And that pattern happens to be 1 plus cosine of 2 times x all over 2. 1 plus cosine 2x all over 2. And so now I'm just going to multiply these together. Now if you notice on top, I would have to FOIL. So there'd be 1 times 1, which is 1. 1 times cosine 2x is cosine 2x. Another cosine x times 1, so cosine 2x. And cosine 2x times cosine 2x is a cosine squared of 2x. That's going to be an issue all over 4 because you multiply across. So everything's fine here except for that last part. I don't like squared, so I'm actually going to take that piece out, replace it again with the formula above. Now be careful. Up here, the original problem says that it's cosine squared of theta. But in our problem, we have 2x. So actually, we're going to need to double 2x. I'm also going to take the 1/4 out, just to make things easier for us. So cosine of 2x, oh, 2 of those, because we have 2 of them, plus 1 plus cosine of 4x all over 2, because I need to double the fact that there's already 2x there. So now what I have here is that now I'm going to have to get a common denominator. So to get a common denominator, I'm going to multiply the first 2 by 2 over 2, the second one by 2 over 2. So I end up with 1/4 times 2 plus 4 cosine 2x plus 1, because now I'm moving into here, plus cosine 4x. All of this can be written over 2 now. Notice that we now have some common terms on top, the 2 and the 1. And what they're going to do is they're going to take this extra 2 that you're dividing by and move it up front. So I get 1/8 times 3 plus 4 cosine 2x plus cosine 4x, because those cosines are not like terms, and you are done. The next set of identities are the half-angle identities. So if I know that I have an angle of like 15, I got to figure out the exact value of it. I can figure out this exact value by saying, wait a minute, 15 is 30 divided by 2, and therefore theta in our problem would be a 30, not 15. The biggest thing is that a lot of these have plus or minus in front. And the true reason is that you need to worry about where does the initial angle lie, which quadrant, and the sign on that angle. So the first problem we have is sine of 75. What you need to realize is that 75 is not on a unit circle. We could take 30 plus 45 and use the sum and difference formulas for sine. But instead we're going to say, wait a minute, 75, isn't that the same thing as sine of 150 over 2? And if that's true, that means I can use the 150 as the theta up in our problem. So this would equal, and remember 75's first quadrant, it's positive, so it's going to be the same thing as 1 minus the cosine of 150 all over 2. 150 is definitely on my unit circle. The cosine of 150 is a negative number because it's in the second quadrant. So it equals the square root of 1 minus a negative square root of 3 over 2 all over 2. Negative negative makes a positive, so I'm going to go over here. and become 1 plus the square root of 3 over 2 all over 2. What we have is a complex fraction inside there, so I'm going to take care of that by saying, wait a minute, 2 is really 2 over 1, and I'm going to multiply by the reciprocal. So I get 1 plus the square root of 3 over 2, and that whole thing is going to be multiplied by 1/2. And if I do that, I end up with 1/2 plus the square root of 3 over 4. And if I want to get a common denominator, 2 and 2, so I get the square root of 2 plus the square root of 3 over 4. And wait a minute, when I'm square rooting a fraction, I can square root the top over the square root of the bottom, which becomes square root of 4, which is 2. And we have an answer. It's okay to have a square root within a square root, because that's the exact answer. The next one is a tangent. Tangent has 3 options. 7 pi over 12 would actually be pushed into a little bit further into the second quadrant. Tangent's negative. Because I can see that really easily, I'm going to choose the top problem, and I'm going to actually find out what theta is and then use the one with the square root. It will not matter. As long as I know what theta is, the sign will come along. Now, how do I know what angle that was cut in half would result in 7 pi over 12? Well, then just multiply it by 2. And if I multiply by 2, I get a 6 in the bottom. So theta itself is 7 pi over 6. So I start off with a negative 1 minus cosine 7 pi over 6 over 1 plus cosine 7 pi over 6 equals a negative square root of 1 minus 7 pi over 6 is on the unit circle. I do believe that's a negative square root of 3 over 2, so I'm going to make that a positive, and then 1 minus the square root of 3 over 2, because it's going to change the signs. I'm already doing that to kind of save myself some time and some space. This is going to equal a negative. Now, in this case, I'm not going to flip and multiply. I'm actually going to multiply the top and bottom by the LCD. The LCD is 2, so I'm going to multiply by 2 over 1, and then I'll distribute it in. So when I do this, I end up with the square root of 2 plus the square root of 3 all over 2 minus the square root of 3, all inside. Now, officially, we should possibly multiply by the conjugate to get rid of the square root on the bottom, but in this case, I'm going to let it be and say that is the exact answer, so we can move on. Okay, the second to last thing we got to talk about are the product to sum identities, and then the next one will be the sum to product. So if I have 2 trig functions that are multiplied, sine, cosine, cosine, sine, cosine, cosine, sine, we have formulas that we can expand or even condense. And so if I have a sine cosine, that is the top right. Don't forget that we have a 1/2 in front of all of these. So we get 1/2 times sine of 4 theta plus theta, and then it's plus the sine of 4 theta minus theta. So it's all about figuring out which A, what's B, or alpha, beta. Alpha is 4 theta, beta is theta in our problem. So it's easy to figure this out. It's just this sine of 5 theta plus sine of 3 theta. And then the book does actually distribute these things in, which is fairly easy. We get problems like this, we're pretty happy. We like those. The same thing is going to happen if we have the x's. So I'm not going to do that problem. It's pretty straightforward on those. The last group is going the other way. What if I have a sum of trig functions? Can I make them multiplied? And the answer is yes, yes you can, as long as we are following the rules. Now I'm going to skip over the first one. This first one, because the directions say use the product to sum or sum the product. This one's a product, so therefore go to the product to sum, which is the last problems that we did. This time we have numbers and you actually find exact answers. So we'll do part B. Part B says, hey, wait a minute, it follows this pattern here of a cosine minus a cosine. Now remember, it is in radians, it's okay, but it becomes negative 2 sine of 7 pi over 12 minus pi over 12, or plus pi over 12, all over 2. And then sine of 7 pi over 12 minus pi over 12, all over 2. So as I work this out, I end up with 8 pi over 12 over 2. And sine of 6 pi over 12 over 2. And when you're dividing a fraction by 2, it's like multiplying by half. And if I multiply by half, that means I'm actually going to double the denominators. So it's negative 2 sine of 8 pi over 24 sine of 6 pi over 24. I don't have pi's over 24s. So what I'm going to do is like, hey, wait a minute, I can reduce those. So that's a negative 2 sine of pi over 3. I know that one. And pi of, or sine of pi over 4. I know those two. So it's negative 2 times square root of 3 over 2, square root of 2 over 2. Start to simplify. 2 and a 2 cancel. So it's a negative square root of 6 over 2, and you have your answer. So this one's all about just using the identities. Your homework. So homework 5.5. What we have here is page 352. You guys should have done 16, 18, and 20. And then on page 352, day 2, I want you guys to do 1, 5, 29, 31, 37 through 43 odd, and 57 and 69. Have a great day.